To learn the partial fractions technique, we're going to break down rational functions into a couple of categories. Those denominators which have linear factors, that's what we'll study in this video, and those denominators which have quadratic factors, that's coming in the next video. As for linear factors, we need to know, are they distinct or are they repeated? So we're going to begin with the simplest possible case, that is a rational function which has distinct, that means unrepeated, linear factors in the denominator. The form that you see listed there looks a little bit intimidating, but we want to look at the overall structure in order to interpret the process by which we will break down a complicated fraction like this into simpler components. So the form that we will consider has a function of x in the numerator. So that can be any sort of function of x, and it will not affect the way we split up our fraction. We will take the denominator and factor it as far as possible. So notice in this form, each individual factor is linear, and by linear I mean the highest power of x that we can find is x to the first power. Notice the coefficients a sub 1, b sub 1, a sub 2, b sub 2. Those represent real numbers, and the subscripts there help us to distinguish one unique factor from the next. So when I have factored a polynomial denominator into distinct linear factors, then I'm going to split it up in a certain way to begin developing the simpler components. Notice on the right side here we have the sum of several fractions. So we're going from a product over here to a sum over here. Each distinct fraction contains one of those unique linear factors for its denominator. So I'm going to introduce a partial fraction for each unique linear factor from the original denominator. And then I'm going to have an arbitrary constant. Notice the capital A here as opposed to the lowercase coefficients in the denominator. That's going to be an arbitrary constant. So if we have a unique linear factor in the denominator, we will assign an unknown constant in the numerator. Same thing here. If we have a unique linear factor, I'm going to assign an unknown arbitrary constant for the numerator. And we'll do this for as many unique linear factors that we have. Now, for the general form for this notation, I have subscripted the coefficients, the lowercase a and b, the uppercase a, in order to keep it very general. But as you'll see in practice, we're going to simplify that just a little bit. So let's apply this process to example 1. We have the integral of 1 over 4x squared minus 9 dx. Notice we have the difference of two squares. The function of x is first, the constant is second. That reminds us a little bit of the arcsecant formula, but we don't have all of the components. Remember, if that were under a radical with the same function of x outside the radical, we would recognize that as an arcsecant. If we had the sum of two squares, 4x squared plus 9, we would recognize that as an arctangent. But again, this particular rational function doesn't fit either of those categories, so we're going to handle it with partial fractions. Now, I'm not going to integrate at this moment. I'm going to do a little bit of algebra. So I'm going to take the radicand out and begin working on it. In fact, what I want to go ahead and do is factor this denominator into linear factors. It factors as 2x plus 3, 2x minus 3. So notice we have two unique linear factors. So I'm going to introduce a partial fraction which contains the denominator as one of those unique factors. Let me say it this way. Each unique factor becomes a denominator of a partial fraction. Now, because we have a linear denominator, we're going to have a constant numerator. The numerator will always be 1 degree less than the denominator. So I'm going to call the first unknown constant a and the second unknown constant b. You can subscript those constant, call it a sub 1 and b sub 1, but the notation's a little easier if you simply use different letters. So the idea is the original fraction is the result of adding two simpler fractions together. At this point, our goal is to find those unknown constants. Find a and b. To do this, we're going to clear fractions on both sides. So I'm going to multiply both sides by the LCD, which of course is the product of our two denominators here. Got a little workspace here. Again, I'm just multiplying both sides by the LCD, lowest common denominator. So on the left side, you can see both of those factors cancel, and that leaves behind a 1 on the left side. Now on the right side, I'm going to distribute this lowest common denominator to each term. Notice when I distribute it to the first term, the 2x plus 3 cancels, and that leaves behind a times 2x minus 3. For the next fraction, we will again distribute our lowest common denominator, and in this case, the 2x minus 3 cancels, leaving behind b times 2x plus 3. Now at this point, we are dealing with something called an identity equation. That means this equation is true for all x. We could say true for all, remember the upside down a means for all x. So no matter what x value I plug in there, I should get a true equation. So what I'm going to do is choose a convenient x value to plug in that will allow me to solve for the unknown constants a and b. Convenient values to choose are the zeros of those individual factors. So I'm going to look at that first factor, and I'm going to let x equal 3/2. That's the zero of this factor. That is, if I set that factor equal to 0 and solve for x, I would end up with 3/2. So we'll plug 3/2 in for x. Now on the left side, I still have this 1. Notice when I plug 3/2 in for x right here, I'm going to get a 0, and that entire term is going to cancel out. On the second term, we're going to have b times 2 times 3/2 is 3, and 3 plus 3 is 6. Notice this yields an equation in one variable, and we'll be able to solve for b. In this case, we can see b is equal to 1/6. And by the way, I'll show you a couple of methods for solving for these undetermined coefficients. This happens to be our first method. Now, my next goal is to find a. So I'm going to choose another value for x, and this time let's use the 0 of our second factor. That is, if I set that factor equal to 0 and I solve for x, I would end up with x equals negative 3/2. So plugging x equals negative 3/2 into this equation, we have 1 equals 2, right here, 2 times negative 3/2 is negative 3, and negative 3 minus 3 is negative 6. And if I plug negative 3/2 in here, that term zeroes out. And notice we can then solve for a. A is negative 1/6. So the reason this particular method works, we're using one equation which seemingly has 3 unknowns, but we're using the fact that this is an identity equation. That is, it's true for every possible x that we plug in, and therefore we can choose convenient x values to solve efficiently for a and b. So now we're going to return to our model. We started out with the original integrand. Of course, it was in factored form. And now we're going to rewrite our integrand using this split form and the new values for a and b. So we can see that the original problem, 1 over 4 integral of 1 over 4x squared minus 9 dx, can now be written as the integral of a is negative 1/6, over 2x plus 3. So that's this first partial fraction, plus the second partial fraction, b is 1/6. Its corresponding denominator is 2x minus 3 dx. So using this preliminary algebraic technique of partial fractions, we have taken a more complicated rational function and we have broken it down into 2 simpler components that will be easy to integrate. So let's work on these integrals. We could rewrite this first one as having a coefficient of negative 1/6, 1 over 2x plus 3 dx. And the second one, we can give its own integral sign as well. We'll factor out the constant, and we need to evaluate integral of 1 over 2x minus 3 dx. Do observe that each of these new integrals will require a u substitution. We'll let u equal the denominator, and recognize that du is 2 dx, and dx then will be replaced with 1/2 du. We will also need a substitution for this second integral, but to keep my variables straight, I'm going to go ahead and use v on this one. We'll let v equal 2x minus 3. dv then is 2 dx, so we'll replace dx with 1/2 dv. So now in terms of u, the first integral becomes -1/6 times the integral of 1 over u times 1/2 du. And the pattern of our second integral is 1/6 times the integral of 1 over v times 1/2 dv. You will recognize both of those integrals as having a natural log for the integrand. Now, combining our constants, we have -1/6 times 1/2. That's going to give me a coefficient of -1/12, and the antiderivative is the natural log of the absolute value of u. A similar procedure occurs on the second integral. 1/6 times 1/2 is 1/12, and the antiderivative is natural log of the absolute value of v, and we can go ahead and add our constant of integration here. At this point, we can go back and recover our original variable. U, remember, was 2x plus 3, and v was 2x minus 3. Now that is an acceptable answer, but we can also condense it if we wish. I'm going to factor out a positive 1/12. Now, when I factor out a positive 1/12, I'm going to start with my positive term, that's natural log of 2x minus 3, and subtract natural log of the absolute value of 2x minus 3. Oops, 2x plus 3. So I'm just changing the order of those natural logs so that I can lead with the positive. Then we can condense those natural logs by finding the quotient of the argument. So we have natural log of the absolute value of 2x minus 3 over 2x plus 3 plus arbitrary constant c. So by prepping the initial integrand, using this partial fractions technique, we were able to take this cohesive fraction and break it down into two easier to integrate integrands. We made a u substitution for both, and now we have an antiderivative. So we're not necessarily looking at a new integral technique. We are looking at how to prepare the integrand with algebra in order to simplify the integration process. Now, let's consider the second category when we're dealing with linear factors. What happens when one of those linear factors is repeated? So in the model, again, we're not really that interested in the numerator. It can be some sort of function of x. It may even be constant. But what we're recognizing is that we do have a linear factor in the denominator, but it repeats n times. That is, I am raising it to a specific power. So the way that we're going to develop our partial fractions in this case is we're going to have one partial fraction for each ascending power of that linear factor up to the highest exponent. And in each case, because we're dealing with a linear denominator, we will assign an arbitrary constant to the numerator. In the case of this general form, we're using subscripted a's, so we can have a general number of partial fractions, but in practice, we'll probably call those constants a, b, c, and so forth. So let's try this on example 2. We have the integral of 4x squared over x cubed plus x squared minus x minus 1. Notice an ordinary u substitution for the denominator would not work because the numerator has insufficient terms, and this certainly doesn't match any of the patterns that we've studied in this class up to this point. So our goal is to take the integrand out and begin simplifying it or separating it into partial fractions. Now, in order to do this, we need to know the factors of the denominator. Well, we've got 4 terms in the denominator, so we're going to factor by grouping. You can take an x squared out of those first 2 terms, and that leaves behind an x plus 1. We're going to take a -1 out of the second 2 terms, and that leaves behind x plus 1. Then, if I look at this as having 2 terms, they have a greatest common factor of x plus 1 in common. And when we extract that, that leaves behind x squared minus 1. So again, I'm just factoring by grouping there. In the denominator, we have a factor which is the difference of two squares. It factors as x plus 1, x minus 1. So notice that gives me a repeated linear factor. We could write this as x plus 1 quantity squared times x minus 1. So I have a repeated linear factor and I have a unique linear factor. So now that we've identified the factors of the denominator, we want to begin developing our partial fraction. So in factored form, the integrand is 4x squared over x plus 1 squared times x minus 1. So I'm going to assign a partial fraction for the first linear factor, which is x plus 1. But because it is a repeated factor, I'm going to introduce another partial fraction for the square of that factor. And then finally, I need a partial fraction for the last unique linear factor, which is x minus 1. So once again, we are dealing with an identity equation. That is an equation that is true for all x, for which of course this function is defined. So I'm going to clear those denominators by multiplying both sides of this equation by the common denominator. And the common denominator is x plus 1 squared times x minus 1. So we're going to apply this to both sides of this equation. Now, on the left side, when I multiply by the LCD, all of the denominators factor, and it simply leaves behind 4x squared. On the right side, we're going to distribute this lowest common denominator to each fraction. When I distribute it to the first term, notice we'll have an a left over. One of the x plus 1's cancels, leaving behind the factor x plus 1 and the factor x minus 1. Distributing to our second partial fraction, in this case, we notice that both the x plus 1 factors cancel, and that leaves behind x minus 1. And finally, we have distributing our lowest common denominator. We observe that the x minus 1 cancels, and that leaves behind x plus 1 squared. Making use of the fact that we're dealing with an identity equation, we should be able to choose any value for x and still have a true equation. So I'm going to choose convenient values for x. And by convenient values, I'm talking about the zeros of the factors that we see. So we'll start with x equals -1. When I plug -1 in for x, we're going to end up with, on the left side, 4 equals, because 4 times -1 squared is 4. And notice when I plug in -1 here, I'd get a factor of 0. That whole term goes away, and the same is going to be true for the last factor. So we end up with b times -2. So we can go ahead and solve for b, and we obtain b equals -2. Another convenient x value to use would be x equals 1, another 0 of one of the factors. So plugging 1 in for x, we have 4 times 1 squared, which is 4. Notice plugging 1 in here would zero out that entire term, and the same thing here as well. So we end up with c times 1 plus 1, or 2 squared, which shows us that c equals 1. Now, we've used all of the zeros of the factors that are present, so I'm just going to choose any random x value. Well, not that random. I want something that's easy to work with, so I'm just going to choose x equals 0. If we plug 0 in for x on the left, we have 4 times 0 squared, which is 0. Then we have a times, I'm just plugging 0 in for x, a times 1 times -1, plus b times -1, again plugging 0 in for x, and c times 1. Now remember, we've already found the value of b and c. So simplifying here, we have -a minus, I'm going to replace b with the value that we previously found. We discovered from the first step that b equals -2. And from our second step, we discovered that c equals 1. So we end up with a linear equation in one variable. We can solve for a, and we end up with a equals 3. Now we're ready to go back and integrate. We have properly prepared our integrand, simplifying it with algebra. Now we're ready to apply some calculus. So the original problem was the integral of 4x squared over x cubed plus x squared minus x minus 1 dx. But we're going to separate that integrand according to this model. So we found out that a equals 3. So we're going to write our first factor as 3 over x plus 1. And I'm going to go ahead and split up the integral as we go. The second factor that we discovered, b equals negative 2. So let's go ahead. Well, I'll just put it on the top. Negative 2 over x plus 1 squared dx. And then finally, we discovered that c equals 1. So our last term looks like the integral of 1 over x minus 1 dx. Notice the first integral and the last integral will yield natural logs. The second integral, however, we will need to make a u substitution. So notice on the second integral, we can let u be x plus 1, du then is dx. So I'm going to go ahead and integrate our first term. We're going to end up with 3 times the natural log of the absolute value of x plus 1. And then I'm going to write my second integral in terms of u. I've got a coefficient of negative 2, and we can rewrite this as u to the negative 2 du. As for our third integral, it has a very easy to recognize antiderivative, natural log of the absolute value of x minus 1, and we'll get our plus c in there. So we're doing a little bit of multitasking here. Hope you're keeping up with me. If you want to do one integral at a time, I think that's a great idea. Okay, let's go ahead and integrate with respect to u. Applying our power rule, we'll get u to the negative 1 over negative 1. And I'm just going to carry this last term along. And simplify, we have 3 natural log of the absolute value of x plus 1. We can call this plus 2 over u, and u, remember, was x plus 1 plus natural log of the absolute value of x minus 1 plus c. Now, this is certainly an acceptable answer, but let me give you a variation or another option. How about this answer? 2 over x plus 1 plus the natural log of the absolute value of x plus 1 cubed times x minus 1 plus c. Now, how did I get to that? Well, I rearranged my terms, I applied some logarithmic properties and condensed the logarithms, right? Moved the coefficient to the exponent and then condensed the sum of 2 logarithms into the logarithm of a product. Either answer would be acceptable. So the big picture of this method is that really it's pretty simple. However, it is extremely detailed and a little bit tedious. So you'll have to practice developing your accuracy because, for example, if you miss a negative somewhere, it can really be detrimental to a problem with this many steps. So at this point, your goal is to see the big picture, know how to separate an integrand that has unique linear factors and repeated linear factors. In the next section, we'll learn what to do with quadratic factors.